Hello, today we're going to talk about energy, what it is, and how waves and particles carry it. Here is a disclaimer. The material is based on sound scientific principles. The opinions expressed here are mine based on the observations we are going to make. This presentation has not been peer-reviewed or accepted by any journal. The information in this presentation is general in nature and not intended as professional guidance, nor will it assist you in passing any exams. You are encouraged to confirm any information obtained from this presentation with other sources. This material is copyrighted. This presentation will address the following ideas. We will define force and energy and discuss how waves and particles carry and store energy. Then we will define waves and present some illustrations of them. Next, we will do the same for particles. Finally, we will compare waves and particles. Particles and waves store and carry energy. Particles carry energy in a ballistic sense. Their movement is defined by inertia and continue in a straight line unless acted upon by an external force. The force that they carry is localized to the particle. Waves carry energy as a sequential displacement in a medium. Without a medium, there can be no wave. A wave is made up of particles. Wave motion can vary with non-uniformities and move along preferred lines, but they generally move outward with a constant speed determined by properties of the medium. Energy is a useful parameter that describes the result of a force that lasts for a duration. This is also known as work. This mathematical construct is very useful in solving a variety of problems. Some of this quantity in a system is often found to be constant. That means that energy is conserved. The simplest definition of energy is force integrated over a distance. This implies how long the force was applied. Another useful parameter is power. This is the rate at which energy is expended or absorbed per unit of time. Power for a length of time is therefore energy. Classic example of energy conservation is the block and tackle. A rope is used to transfer lift to a weight. Number one, the configuration on the left has the shortest pull but requires the greatest force. While number four, the configuration on the right has the longest pull, requires the least force. Product of force and pull is the same for all. There are many types of energy. Kinetic energy indicates the available force due to an object's motion. Kinetic energy of a moving particle can be determined by its mass and velocity as 1/2 the mass times the square of the velocity. A change in velocity implies a transfer of energy to another object, either through a collision or by transformation to another type of energy, such as heat. Potential energy describes how much force or tension is being applied to maintain an object at a certain height or position. If an object is released from some height, its kinetic energy can be predicted from the change in its potential energy as it falls. Thermal energy is a measure of heat, often described as the average motion of particles as in a gas. In a solid or liquid, we mostly mean the average motion of electrons, but the atoms and molecules are also vibrating. Electromagnetic energy is a measure of energy in charged particles. Electric energy is related to potential energy, while magnetic energy is related to kinetic energy. We often speak of this effect on electrons because its mass is so much lighter than that of a proton. The electron moves much more readily. Similarly, voltage and current also relate to the potential and kinetic energy. Product of voltage and current is power, which we mentioned on the previous slide. Energy can be transformed into different types of energy. Transducers are one way of converting energy. Speakers convert electrical energy into sound pressure. Motors turn electrical current into rotation, which is kinetic. Piezoelectrics do the same for voltage into pressure and vice versa, and so on. A wave is a displacement in a medium. This medium is made up of a group of particles that may or may not be bound together. In solids, these particles are tightly bound and hold their shape. In liquids, these particles are loosely bound and do not hold their shape. In gases, these particles are not bound, but in general are confined inside a volume. Waves show the average movement of energy. Particles move back and forth with no net displacement, yet energy is transported in a uniform direction away from the source. Waves have continuous properties and are often used to characterize the statistics of parameters. The following slides will demonstrate these types of waves. Let's consider a spring that is attached at one end to an unmovable wall. Simply compress it. Normally, applying a force would cause the mass of the spring to accelerate it, but the other end of the spring is constrained from moving. The far end reacts by pushing back with an equal and opposite force. This is Newton's third law. Conservation of energy here implies a conservation of force. The sum of the forces must balance since there is no net acceleration. As we compress the spring more and more, the force increases uniformly across the spring. Compression stops when the opposing force matches the compressing force. There is no net motion at this point because we have assumed the spring to be short. Any transient effects happen fast and are damped down. But the spring has mass and mass has inertia. A change in force takes time for the spring to react. For short springs, the force seems to spread almost instantaneously, but this becomes less apparent for a longer spring. Now let's lengthen the spring and detach it from the wall. When the spring is compressed, the inertia in the mass of the spring takes time to react. There is a compression at the starting end, and its compression wants to redistribute across the length of the spring. It compresses the next section of spring, and so on. This compression is expressed along the length of the spring until it reaches the end, where it may terminate or reflect, depending on the conditions at the other end. Eventually, this movement may dampen due to frictional forces. Force applied from the left will accelerate the spring, and this acceleration will travel down the length of the spring. If we were to compress and relax the tension on the end of the long spring, the force will constantly be trying to catch up. The intent is to evenly distribute the force, but it cannot achieve a steady state if the driving force is constantly changing. A wave is a serial displacement due to force that then propagates through the material with the intent of an even distribution of the force. A wave requires a medium for the transportation of force or energy. When the force is in the direction of motion, we call that a longitudinal wave. When the force is perpendicular to the motion, we call it transverse. This graphic shows how energy is transported by waves. In the top animation, we see a longitudinal wave moving across the spring. In the bottom, we see a transverse wave. These definitions refer to the direction of displacement. In this example, a voltage is applied to a circuit. The series elements are inductors, which regulate changes in current. The parallel elements are capacitors, which store and regulate voltage. The result is a wave that flows through the first inductor to charge the first capacitor. The voltage at this capacitor is now greater than those to the right, causing a current to flow through the second inductor to charge the second capacitor, and so on, and so on. The surface of the sea shows transverse waves as ripples along its surface. Waves are produced by the cyclical bunching of particles. Notice the particles in yellow and their circular motion. Their net displacement is zero, yet energy is transported from left to right. The site listed below has many examples of waves and particles. Sound is an example where longitudinal waves transport energy with only a small movement of the medium. Here we see particles moving back and forth with no net displacement. This is another example from the same website as the previous slide. A particle is a small object or cluster of objects. These objects can be described by several properties such as their mass, size, or shape, and any other intrinsic properties. By intrinsic property, we mean any metric that describes its energy, such as motion, tension, electrical charge, magnetic moment, temperature, or any other type of energy. Particles have simple relations between their properties, such as density, which is related to its mass and volume, or kinetic energy, which is related to its mass and motion. The image on the left shows an LED light bulb, which emits red, blue, and green photons. They move radially outward. Noise is present as an uneven distribution of photons at low level. The second slide shows the cyclical emission of particles as one interpretation of radio emissions as photons. It is difficult to classify photons as either waves or particles. This example shows a speaker emitting waves by compression of the air particles around it. They move radially outward. Noise is present as an uneven distribution of signals at low level. The cyclical nature of emission gives the appearance of a wave. The lower the particle density, the more quantum it appears. The higher the density, the more it looks like a continuous wave. Waves and particles can be difficult to tell apart. They both carry energy and move with constant momentum unless acted on. Waves require a medium to travel through. They move at the speed that the medium supports. Speed is often used to determine the properties of the medium. The amplitude of the waves attenuate with distance due to spreading. Particles do not require a medium. Their speed is dependent on their kinetic energy. Particles do not spread like waves. Their energy does not attenuate. Rather, the particle density decreases per unit area due to the spreading into an increasingly large volume. Small particle densities behave like quanta, and large densities behave like waves. We've defined waves and particles. They move in similar ways and can be hard to tell apart. It carries force and energy. In the next video, we will demonstrate the duality of particles and waves. This will lead to explanations of electrical current in a wire, the double slit experiment, and quantum tunneling. If you found this presentation interesting and or informative, please like and subscribe. Thank you.